Okay, welcome back. I'm sorry for the call. So welcome back. Let us start today's class. So if you recall, in my last class, I was doing your maximum and minimum values of a function of two variables, function of two variables, something like f of x, y. Okay, and what we did, we considered the value of the function in a domain D, but we didn't say anything about that domain. I mean, what properties that particular domain possesses. Okay, so you know that, I mean, if we are to find the maximum or minimum values of the function in a domain D, so what we do, firstly, we equate the partial derivatives of the function at partial derivative of the function to 0, right? And from there we find out the critical points, okay? And at the critical points, again we check whether this xx, that is the second order partial derivative of f with respect to x, it is greater than 0 or less than 0. And before that, what we do at that critical point, we check the value of d of xy, and this is simply fxx fyy minus fxy whole square. Okay, so now for the existence of maxima and minima, if you recall, d has to be strictly greater than 0. Okay, and then if your fxx is also strictly greater than 0 at that critical point, so we say that the function has a minimum there, and if this one is less than 0, we say that the function has a local maximum, and if your d is less than 0 at the critical point, so then the function neither has a maximum nor a minimum. Okay, and we designate those points as saddle points. Okay, so now the question is, we didn't say anything about the domain D before. We didn't say about this domain. Okay, so now if you recall, for a function of one variable, it will consider a closed set. Okay, a closed set in R. It is nothing but what? It is simply a closed interval, right? And you know that at a closed interval, the extreme values of the function exists, right? So it is going to exist either at some point inside the interval or at the boundary points. Is it okay? So earlier, what happened for a function of one variable, when we consider the interval, the boundaries were nothing but the two endpoints. Okay. So likewise, what we can do, we can also define closed set as a domain D in R2, and a closed set is a set which contains all its boundary points. Okay, which contains all its boundary points. So now then again you are going to ask me, I mean, what are the boundary points? Okay, so now say suppose I'm considering a domain, this one. I'm considering a two-dimensional domain. I'm considering a domain like this. Okay, and obviously you can see that this shaded portion is the domain I am considering, and I am drawing its boundary here. I am drawing its boundary which is drawn by using blue color here. Okay, so then, I mean, if I consider the set of all points lying on this boundary, so what property does it have? If you consider a very small disk centered at a boundary point, say suppose a boundary point is AB, and I am considering a disk designated by this center at this point, then it is going to contain points belonging to both D and not also
complement.
Yeah, not also belonging to this domain, isn't it? So if there exists, if this contains at least one point which does not belong to this domain, then we say that this point AB is a boundary point. This point AB is a boundary point. Okay, and all the other points belonging to D, which are non-boundary points, they are called interior points. Okay, so the definition of boundary points is clear like this. So now, if I consider, suppose, I mean, if I consider D to be the set of all points belonging to R2, such that x squared plus y squared is less than equal to 1. So what it is nothing but a circle of radius 1. Okay, a disk. Okay, a disk. It represents a disk, right? Which is nothing but the set of all points lying inside the circle x squared plus y squared equal to 1, and also all the points lying on the boundary of the circle, lying exactly on the circle. Okay, so now when the set is set is going to stop, like say set is not going to be a closed set if it doesn't have even a single point from the boundary, if it doesn't possess that point, even then it is not going to be a closed set. Okay, fine. And then again, there is another concept here. So far we have learned about closed set. Then before that we have learned about boundary points, and then let us consider the concept of bounded set. So what is a bounded set? A bounded set is a set which is contained in a disk, in R2. Okay, so what does it mean? It means that the extent of that set is finite. I'm not talking about the number of points being finite. I'm talking about the extent. Okay, so for example, suppose I consider a set, say D1 of all points belonging to R2 such that x equal to y, right? So then what is going to happen? So this set is going to contain all the points lying in the line x equal to y. Is it okay? Right?
Yes.
So now if you consider all those points, the extent of this set, it is not going to be
Bounded.
what? Yeah, it is not, extent of the set is not going to be finite. So this is not a bounded set. Okay, but this particular example, this is a bounded set. Okay, so now because the next theorem is going to involve the extreme value theorem on a closed bounded set. So that is why I needed to go for all those concepts. Okay, so now let us come to extreme value theorem for a function of two variables. You should remember that. Extreme value theorem for a function of two variables. Okay. So here what we do, firstly, what we consider that f it is a function in a closed bounded domain D and f is continuous. Okay, I am considering this function and okay, fine. So then f possesses its absolute maximum value f of x1 y1 and absolute minimum value f of x2 y2, where your x1 y1 and x2 y2 here they belong to the set D. Okay, so now because say this theorem guarantees you absolute maxima and minima. Earlier, whenever we talk about maxima and minima, in fact, we are talking about local maxima and minima. Okay, and I had shown you some examples where you could see that for some cases, I mean, like say, only the maximum exists in that particular domain, and only the minimum exists in some cases, and in some cases, neither of it exists. Okay, so now if we take F to be continuous in a closed bounded set D in R2, definitely the maximum and minimum value of the function exists. Okay, so now how to go about it? I'm going to how to find it. Okay, so I'm going to just show you a table. Where you will see the procedure. So this is about absolute maximum and minimum on a closed set. For example, what we did here, you can see that these two sets, it contains boundary points as well, so that is why they are closed sets. But here, obviously, this one and this one on the extreme right, they are not closed because they it doesn't have some points belonging to the boundary. And here, we have intentionally eliminated only one point. Even elimination of that point is not going to make this set qualify as a closed set. Okay, so we have already defined boundary points. Then we have already talked about closed set. We have already talked about bounded set. Okay, and this is the extreme theorem for a function of two variables. If F is continuous in a closed bounded set D in R2, then F attains its absolute maximum value this and absolute minimum value this at some points x1, y1 and x2, y2 belonging to D. And this is the procedure. So to find the absolute maximum and minimum values of a continuous function F on a closed bounded set D, firstly what you have to do? Firstly, you find out all the critical points. Okay, and then find the extreme values of F on the boundary of D. Okay, and the largest of the values from step 1 and step 2 is the absolute maximum, and the smallest value of this is the absolute minimum. That's it. It is as easy as that. Okay, now it may sound it is as easy as that, but again, you will see that the problem of finding absolute maximum and minima on a closed set in R2, it is going to depend upon what the domain is. Okay, a function should not be a problem, but you have to examine the domain more clearly. Okay, so what I'm going to do, I'm going to take this example. Find the absolute maximum and minimum values of F on the set D, where D is the closed triangular region with vertices 2, 0, 0, 2, 0, -2. And the function is given as x squared plus y squared minus 2x. Okay, so let us come back to that problem. Okay, so here the function was f of xy given by minus 2x. Okay. And the domain, what it is? It is a triangle. It is a triangle with vertices 2, 0, 0, 2, and 0, -2. 0, -2. Okay. So basically, I have this triangle. Okay, this triangle is my domain D. This triangle is my domain D. Is it okay? Fine. So for your convenience, let me denote these three boundaries as say B1. This is say B2. This is say B3. So B1 is nothing but this side. B2 is this side and B3 is this side. Okay, fine. So now let me tell you the procedure. So the very first thing, firstly find out the critical points in the interior of this domain. Okay, so in order to find out the critical points for this function, so what we'll have to do, we'll have to firstly equate this to 0 and fy is to 0. Okay, so obviously this is going to give you x equal to 1 and y equal to 0. So the only critical point is your 1, 0. Is it okay? Fine. So now again, the next thing is we are not even going to go for whether I mean that could be a local maximum or local minimum, right? Because eventually we'll be interested only in finding out absolute maximum and absolute minimum. So that is why we are not bothered about it, because eventually we are going to find out the largest of all the values of critical points and the boundary points and the smallest of them. So let us try to find out what is f10. So f10 is what? 1 minus 2, right? It is minus 1. Am I okay? Fine. So my first task is done. Let us check it. My first task is done. Now for the second task, what we need? We need to find out the value of the function on the boundary.
On the boundary.
Yes. So now let me come to the first boundary. Okay. That is B1. Fine. And now in B1, say this is B1. This is nothing but a straight line passing through the point 0, minus 2, 2, 0. 0, minus 2, 2, 0. So the what is going to be the equation? Y minus 0, right? This is equal to what? Minus 2 minus 0 and 0 minus 2 x minus 2, isn't it?
Yes.
Right? So basically this is going to give you y equal to x minus 2 eventually. Obviously the slope is positive. Similarly, the equation of this is going to be the same, but the slope is going to be negative. Is it okay? Because this is passing to the same point. So this is going to be y equal to minus x plus 2. You can check it. It should be that. Is it or not? Because this will remain same. Only thing is that it is going to be 2 minus 0, 0 minus 2. Yeah, so it is going to be fine. Okay, so B1, I mean here it is given by y equal to your x minus 2, and you can see the range of x is from 0 to 2. Is it okay? Where your x goes from 0 to 2. Okay, and then what we are going to do? We are going to basically find x, this. Okay, fine. Now this becomes what? X squared plus x minus 2 whole square minus 2x. So x squared. So 1x squared will come from here. Then minus 4x minus 2x. This is 6x plus 4. Okay, fine. And now what we'll have to do? You can see there are many ways of finding the maximum and minimum value of the function in this interval. So what you can do, again, you can apply the extrema value theorem for a function of one variable. I can do in some other way. X squared minus thrice x, 2x 3 by 2 whole square, and then So it is going to be minus 9 by 2 plus 4, right? Yeah. So this is going to be 2 into, is it visible? Yeah. 2 into x minus 3 by 2 whole square, and this is going to be half, minus half. 2 into x minus 3 by 2 whole square minus half. That may not be visible there. So let me write it here. 2 into x minus 3 by 2 whole square minus half. Okay. Let me make this visible now. Okay, fine. So then obviously you can see that if you consider obviously what is going to happen, like the minimum value
It's equal to 3 by 2.
3 by 2. Okay, so what is going to happen? So f, what should I write? F and what point? X is definitely 3 by 2. Y is what?
Three by 2 minus 2.
Yes, so that is minus half, right?
Half.
Minus half. So this is minus half, and maximum value is going to occur at x equal to 0, I guess. Right? Yes?
Yes.
0 minus 2. So that is going to be what? This is going to be 9 by 2 minus half. Right? I think that is going to be 4. Yeah. Fine.
Yes.
Right? So now again you will see that here also it is the same scenario. I mean along B2, again your y is your minus x plus 2, right? And your f of x 2 minus x, this is going to be the same. This is going to be the same. Eventually it is 2 into, because there is y squared. Okay, fine. So as before, it is going to be the same, isn't it? These two, eventually you are going to come across, although the points are going to be different, you are going to come with the same values. Are you getting my point? So here also it is going to be what? F of 3 by 2. If it is 3 by 2, then this is going to be half. So this is going to be equal to minus half, and f of 0, it is 0, 2, that is going to give you 4. Is it okay?
Yes.
Fine. So now let us see what is B3. Okay, so along B3 you can see that your x is equal to 0. B3, x is equal to 0 and y goes from minus 2 to 2. Minus 2 to 2. Right? So that means your f 0y, so this is equal to y squared. This is equal to y squared. Right? So obviously the maximum value is 4, minimum value is 0. Max occurs at plus minus 2. Right? So f of 0 plus minus 2, so this is 4. And f of 0, 0, this is equal to 0. Right? So we are done. So now if you look at this amongst all of them, you can see that this is minimum and this is maximum. 4 is maximum. Is it okay? Fine, because we get 4 in 3 occasions. Is it okay? Fine. So the absolute minimum value of the function is -1 and it occurs at the point 1, 0, and absolute maximum is 4 and it occurs at 3 points, 0, -2, 0, 2, 4 points. 0. Again, see, not 4 points. It is at 2 points because they are eventually the same, right? Isn't it? These are eventually the same point. This here 0, 2. This is 0, 2. 0, -2. This is 0, at 2 points. Is it okay? Fine.
Yeah.
So this is the way. This is the way we are going to find out the absolute maximum and absolute minimum value for a function of 2 variables in a closed set. So the next concept, I'll go a little bit slow about that. That is a very, very important concept. Lagrange's multipliers. Lagrange's multipliers. I'm just going to show you a figure that the next is Lagrange multiplier. Okay, so basically what we are going to do, extreme values by Lagrange's multiplier. Okay, so what we are going to do, we'll try to do it for a function of 3 variables. But in order to, explain the concept, I'm going to use a function of 2 variables, and then I'm going to extend it to function of 3 variables. This can be applied to any multivariable functions. You should remember that. Okay, so for that, let me just show you a very interesting example. So this is the example. A rectangular box without a lid is to be made from 12 square meters of cardboard. Find the maximum volume of such a box. A rectangular box without a lid is to be made from 12 square meters of cardboard. Find the maximum volume of such a box. Okay. So let me come back to this one. So basically, what you have some cardboard, okay, having area 12 meters square. So from here, you have to find out a box without a lid, okay. So it is going to be something like this. It is going to be something like this. Okay. So basically, this box. So there is no lid. This box, there is no lid. Okay. So if I consider the length to be x meter, breadth to be y meter, and height to be j meter, right? So then the volume, now I'm not going to mention about meter. So the volume, which is a function of x, y, j, it is simply x, y, z. Is it okay? Fine. Okay. And the surface area is going to be C. Surface area, what we are going to do? Firstly, we are going to consider this area. So that is simply xy. So then what we have to do? We have to consider this plus this. So this is what is the area of this x? J. So it is going to be 2xj. So similarly, I am going to have 2xy. 2xy. Okay, and what I have been given that I have to find out the maximum of this function subject to this condition. Is it okay? Fine.
Why is there 3 times xy?
Sorry. It is yz. Thank you. It is yz. So I'll be considering this part and this part. Well, you can see that this is yj, 2yz. Yes. Thank you. Is it okay now? So the problem has been defined. So the problem is like if I consider this, okay, now the problem becomes find the maximum value of the function vxyz subject to the condition gxyz equal to some constant, right? Basically, maximize fxyz subject to gxyz equal to k, subject to gxyz equal to k. Okay, so now whatever knowledge we have till now, so what we would have done here, like what we would do. So far we know how to find out the extreme values of function of two variables, right? So what we would have done, from here, what we would do, we would eliminate j, because from here, what you are going to get 2z x plus y. So this is equal to 12 minus xy. So this implies j equal to 12 minus xy, 2 into x plus y, right? And this function, it is not defined at x equal to 0, y equal to 0, right? But the thing is that that can never happen because we are considering the volume of a box, and what xyz being the length, breadth, and height, they are always going to be non-zero. Okay, fine. So now then, what we would do? We will simply convert this vxyz into some function of phi xy. Okay, and then I'll simply I'll do 12 minus xy, 2 into x plus y. I convert into a function of two variables, and then I'll find out the maximum minimum. That's what we would have done. Okay, and eventually I'm leaving it as a homework. You will see that the volume, it will come out as your 4 meter cube. Is it okay? Fine. So now let us come back to this extreme values by Lagrange's multiplier. Extreme values of Lagrange's multiplier with the help of the concept of Lagrange's multiplier. So basically, what this is, it is about something like that. So what now you have to do? See, earlier when we found out maximum and minimum values of function, there were no constraints, there were no conditions imposed. So now, what is new here? You have to find out the maximum or minimum values of function under certain conditions. Okay, so here the condition is this. So that means here the condition was this. Okay, fine. So now let me come back to a function of two variables. Before that, let me just okay. What I am going to do, I am going to take an example of a function of two variables. I will explain the concept, and then I move to a function of three variables. Okay. Fine. So, okay. Now, suppose I'm thinking about a function of two variables. Say, suppose you have to maximize or minimize f of xy subject to some condition g of xy. This is equal to k. This is equal to k. Okay. So now let me try to draw roughly. Suppose this is my domain of definition of the function. Suppose this is D. Suppose this is D, and I am defining a function. And obviously, you know that the graph of the function, it is going to be a surface. And suppose the surface is something. Surface looks something like this. Surface looks something like this. Okay, surface looks something like this. Okay, so this is nothing but graph of the function z is equal to f of xy. Okay, so obviously the way I have drawn the function here, obviously this is the point of maximum, isn't it? This is the point of maximum, right? But now the question is, it is not about finding this point. It is about finding some points where the maximum or minimum value of the function occurs subject to this condition. Okay. So now, can you tell me? I mean, g of x comma y equal to k. What does it represent?
A curve.
Yes, it represents a curve in xy plane. Okay. So that means what I am going to have. Say, suppose this is the curve. Suppose this is the curve. Your g of xy equal to k. G of xy equal to k. So now, see, suppose I consider this to be the point of maximum. So if I draw a plane, I mean parallel to j passing through this point. So probably it is going to generate some closed curve like this, the way I have drawn, right? So here it is going to be maximum, or it is simply going to be a point if the plane is going to be tangent to the surface at that point, isn't it? Is it if or if it has to? It has to, right? If I think about the maximum value of the function without any constraint, right? So I mean, corresponding to that, I'm going to get a point here. And then if you I mean successively intersect this surface with planes parallel to z-axis, what it is going to give you? It is going to give you what? It is going to give you some
Circles.
yeah, circle or some closed some closed curves, which are nothing but the level curves, right? So eventually, what is going to happen? You are going to find a level curve of the function which has to be maximized or minimized, which touches the function given by this constraint. Okay, so at that point, your maximum or minimum value is going to occur. That is the case. Okay, so if the concept is not still clear, what I'm going to do now, I'm going to show one example. From there, it will be absolutely clear to you. Okay, so let me show you this example. Okay, so consider this example. Find the points on the rectangular hyperbola xy equal to 1 that are closest to the origin. 0, 0. Okay, so let me first work out the problem, and after that I will come back to similar figures like whatever I have just explained in the blackboard. Okay, fine. So we have to find out the points of the rectangular hyperbola given by xy equal to 1, which are closest to the origin. to the origin. Okay, so I mean without any geometry, I'll just mechanically I'll do this problem, and after that I'll come back to the geometry of this. Okay, fine. Let this figure remain. I'll try to work it out here. I'll try to work it out here. So if you consider any point xy, if you consider any point xy in xy plane, and if you want to find out its distance from the origin, what it is going to be? Yes?
Root over x square plus y square.
Root over x square plus y square. Okay. Root over x square plus y square. Right? So basically what we have to do, we have to maximize. We have to maximize here. We have to minimize here, right? Because we are seeking the point closest to the origin, right? The closest, that is the shortest distance we are trying to find out from the origin, right? So what we are trying to do, we are trying to minimize this function. We are trying to minimize this function subject to this condition. Is it okay?
Yes.
Or we can simply think about, say, minimizing square root x square plus y square is similar to minimizing x square plus y square. So simply we can think about this function. Basically, we have to what? We have to what? Minimize this function subject to this condition. Is it okay? Because here it is only about finding out the points. Okay, finding out the points closest to the origin. Right? So now, then what we'll do? So this is exactly like the problem that we posed earlier, right? So here your g of xy is simply this xy, isn't it? So now what we have done, as before, I would have converted this f of xy into a function of say x with the help of this constraint, So x squared plus, so y is from here, it is going to be 1 by x, so 1 by x squared. So I'm going to get your x to the power 4 plus 1 by x squared. Okay, so now if you want to find out the critical points, let me guarantee you that you are going to get them as x equal to plus minus 1. Okay, you can easily find it out, right? Find out the derivative of this and equate it to 0 and you are going to get it, right? So since your y is equal to 1 by x, so the points we have found out is simply 1, 1 and minus 1, minus 1. Okay. So basically what is going to happen, this is nothing but a rectangular hyperbola. So at these 2 points, that rectangular hyperbola is going to be closest to the origin. Is it okay so far? Is it okay?
Yes.
Fine. So now
Yes, sir.
let us come to the pictorial explanation of this. Okay. So now you simply look at this figure. So this is what is happening. Here, the blue lines, they represent the rectangular hyperbola given by xy equal to 1. Okay, that is nothing but the constraints like gxy equal to k. Okay, and then this red curve, which is nothing but a circle, it is nothing but of the function has become tangent to the given constraints. Is it okay? Fine.
Then you could not be hurt for 2 minutes.
Am I audible now?
Yes.
Okay. See here the blue line is nothing but the constraint given by xy equal to 1. That is nothing but the rectangular hyperbola. Okay,
Yeah.
and the red closed curve, which is a circle, it is nothing but a level curve of the function x squared plus y squared. So this is simply what x squared plus y squared equal to 1, isn't it? F of xy equal to 1. Okay, and you can see that both these curves, the red curve and the blue curve, they are tangent at the point of minimum here. Is it okay? Fine. So that is the concept we are going to use in Lagrange's multiplier. The concept of Lagrange's multiplier is going to come from that. Okay, let me tell you what is happening out here. So now, if I consider a tangent to the red circle at this point, and also if we consider tangent to the blue curve at this point, okay, so then what is going to happen? The tangents are
going to coincide.
Or they are nothing but they are parallel. Is it okay? Fine. They are parallel.
Yes.
Is it? They are going to be parallel. Okay. Or I mean, you can say that they are going to coincide. So if we consider the normals to the curve at the point of maximum here at the point of minimum, so then what is going to happen? Those normals are going to be parallel to each other. Is it clear? Yes?
Yes.
Fine. So that is the concept. That is the concept that is going to be used. So what is happening out here? What is happening out here? I have a function f of x, right? So then you know that earlier what we did, what we considered, we considered a function of 3 variables. We considered a function of 3 variables x, y, z, and then we found out that grade f at the point x naught, y naught, z naught, it is a normal to the level surface given by this. Is it okay? Fine. So similarly, the normal to the level curve of this function is going to be given by grade f at the point x naught, y naught, right? Similarly, for the constraint gxy equal to k, a normal is going to be given by this at the point x naught. It seems to be some technical glitch. Let me redo this stuff again. So we were into the tangent lines and the normal to those tangent lines. Okay. So I have already explained it to you. That your grade f at x dot y dot, it is going to be the normal to the curve given by this function. Okay. And similarly, grade g at x naught, y naught, it is going to be the normal at the point x naught, y naught to the curve given by this gxy equal to k, right? So since they are parallel, one must be the scalar multiple of the other. So that is why grade f at x naught, y naught is equal to some non-zero constant lambda into grade g x naught, y naught. Why should lambda be non-zero? What is going to happen if lambda is equal to 0? So we want to.
It's going to be 0 vector.
Yeah. So that means we don't have any direction at all, right? So that is why lambda has to be non-zero. Okay. So now this is the concept that I can use to describe a function of 2 variables. how to maximize or minimize a function of two variables under certain constraint, right? So similarly, if we consider a function of three variables, say function of three variables, f of x, y, z, and if I have to, extremize, like maximize or minimize this function, subject to some constraint, g of x, y, z equal to k, g of x, y, z equal to k. So then what must happen? As before, what must happen? Like the level surface coming out of this, and this is already a level surface, okay? Because this is a fixed level surface. But you know that what is going to happen here, I can have infinite number of level surfaces, okay? And one of them, say suppose this is equal to C1, it touches this level surface at the point of extrema, right? So then likewise what must happen? At that point, if we consider a tangent plan, to those two surfaces, they must coincide at least in the neighborhood of that point, right? So then what is going to happen? Again, if you consider the normal to the tangent planes at that particular points, they must be parallel to each other, right? So that means for this problem also, maximizing or minimizing f of x, y, z subject to this condition, what we must have at the point of extremum, your grade f at x naught, y naught, z naught must be equal to lambda grade z x naught, y naught, z naught. Is it okay? Fine. So this lambda is called a Lagrange's multiplier. This lambda is called a Lagrange's multiplier. Okay, Lagrange multipliers. Fine. Whether you call it Lagrange's or Lagrange, apostrophe s you can use, or you can simply use it as a noun. Okay. So now let me come back to that same problem. Let me come back to the same problem. What was the problem? Finding the volume of a box subject to this condition, xy plus 2xz plus 2yz, right? This is equal to here. So basically what I have gxyz equal to this, okay? And for your convenience way, let me convert it into this. So maximize f of xyz given by this subject to this condition. So if I use the concept of Lagrange's multiplier, then what is going to happen? Your grade f at your x naught, y naught, z naught, where this is the point of an extrema. So I must have lambda grade z x naught, y naught, z naught. Okay, and if I use this notation, then what is going to happen? So this is simply y naught, z naught, and maybe I can convert it later. Unnecessarily again, dot I have to write again, which is very clumsy for me. So yz, and then this is zx, xy. So this is going to be so here y plus 2z, right? And then x plus 2z again, right? And then from here 2x plus 2y, 2x plus 2y. Okay. So from here it is going to give me yz equal to lambda into y plus 2z, zx equal to lambda into x plus 2z, xy equal to 2x plus 2y. Okay, fine. So now, and again, you should remember that we still have one extra condition at hand. Okay, and that is your xy plus 2xz plus 2yz. So this is equal to 12. I may use it or I may not use it later. Okay, so basically, what is happening here? You have to find out the point of extrema with the help of this. Now, when you are going to do that, what may happen? It may happen that you may need the value of lambda, or you may not even need it. Okay, so depending upon this equation, we are going to proceed. So there is no hard and fast rule. You have to remember that. It is going to depend upon the problem under consideration. Okay, so now here, what we are going to do, make some easy way out. So for that, what we are going to do, I am going to multiply this by x, this by y, this by j. So this is going to be xy j dash, xy j y, xz yz. Okay. So then from the first two, you can see that your 2j dash equal to 2zy. So this implies x equal to y, because since we are considering volume, your j cannot be 0. Similarly, x and y also cannot be 0 as well as cannot be negative. Okay, so we have found out this x equal to y. So now can we get something from 2j? Yeah, here I have the same thing. So from these two, from the second and third, what we are going to get, xy equal to 2xz, right? Right. So this implies your y equal to 2z. So this implies z equal to y by 2. Fine. Is it okay? So now, if I use this, z equal to y by 2 and x equal to y here, let me convert everything into x. So then this one is going to imply your x into x, this one 2x, because z is y by 2 and y is x. This, and again y is x, z is x by 2, so this is 12. So now you will see that everything will get converted into x squared here. So 3x squared equal to 12. So that means your x squared equal to 4. So x equal to plus minus 2. Since x cannot be negative, so x is going to be equal to 2. So what we get, x equal to y equal to 2, your z equal to 1. Right? So therefore, the maximum volume is going to be xyj, that is nothing but 2 into 2 into 1, that is 4. Okay, so you can see that both these approaches, it is going to lead you to the same result. Is it okay? Fine. So what I'm going to do, I'm just simply going to finish it here. Maybe I will show you a couple of more examples, and in my next class, I'm going to do. It is not necessary that you are going to find out, or you are going to maximize or minimize the function subject to only one constraint. So it may be more than one constraint. So in that case, what we are going to do. So in my next class, so that is what I'm going to do. But before that, let me just show you a couple of more examples. Okay. So this is what I explained. So I in fact what I did, I drew the surface. So these are nothing but the level curves coming out of the surface. So you can see that if it has to be under that constraint, so they have to touch. This I have already explained. Okay. So and this, in fact, this concept I have already done while doing the tangent plan and normal vector concept. So that is why I didn't repeat it, but you can still go through it. Okay. And then this is the way you are going to use Lagrange's multiplier. So this is what it is. This equation is called the number, sorry, lambda in this equation 1 is called Lagrange's multiplier. And again, remember, these, I mean, this cannot be 0, otherwise we are going to lose the normal direction. So this I have already told you. And this is also a very interesting example. Since I have already uploaded my lecture slide in the class material section, you can go through this. You can have a look at this. Okay. So then next thing, I think this is a part of your tutorial sheet as well. So it is going to be discussed in your tutorial classes. Okay. So probably, I mean, this one you'll be able to use again Lagrange's multiplier, or converting, I mean, like say function of 3 variables into a function of 2 variables also. You can check this. Okay, so this